This is exercise 11 from chapter 8. Suppose that insurance companies did do a survey. They randomly selected 400 drivers and found that 320 of them claimed to always buckle up. We're interested in the population proportion of drivers who claim that they always buckle up. So how are we going to approach this problem? Well, part A is asking us for a bunch of statistics. And here it looks like X, we want to find out what X is. X looks like it's going to be the number of successes that we have. And we'll talk about successes in this scenario. But for us, X is going to be 320. N is going to be the total number surveyed, 400. And P prime here is asked, P prime is going to be the number of successes divided by n. And so let's punch that in our calculator. We get 320 divided by 400. And so we get 0.8. Now if this looks kind of familiar, it is pretty much the binomial distribution. So define the random variables x. So x is in fact going to be our binomial distribution. In words, let's first talk about this in words. X is going to be the number of drivers who claim that they always buckle up. X is number of drivers who claim to always buckle up. And then P, or this is capital P prime. Let's put a little mark down here to say it's capital P as opposed to little p, is going to be the proportion of drivers who claim to buckle up. They asked us which distribution should we use for this problem. Well, since we're going to make a confidence interval for the population proportion, it seems to make a lot more sense to use our P distribution. So we should be using that. And I think one of the things that they asked for maybe in the homework set is to describe this distribution. So let's take a moment to talk about these distributions here. Let's remember that X is a binomial distribution. And remember the notation for that is that we get a little tilde, B for binomial, and then we look for the N and the P. It looks like N in this case is going to be 400. And P is the proportion, and we don't have a set P, and so we're just going to have to use a point estimate P, which is 0.8. It turns out that if we have a binomial distribution that has an N that's large enough and P that's not, that's fairly close to 0.5, that combination there would allow us to be able to estimate our random variable x to be approximately normal. And if you recall, the normal distribution, the binomial distribution, the normal distribution is asking for a mean and standard deviation. And if you remember, if you have a binomial distribution, the mean can be found by n times p, and the standard deviation can be found by the square root of npq. So this is our binomial distribution. This is a normal distribution that approximates a binomial distribution. Now if we're looking for the proportion, it turns out to be capital X divided by n, and that's how one can write our random variable p, or p prime. and that is going to be approximated with a normal distribution. Now imagine the normal distribution whose mean is n times p, and whose standard deviation is the square root of n times p times q. If you divide n times p divided by n, then you're just going to get p, and so for this particular proportion random variable, our normal distribution will have a mean of p and a standard deviation of square root of n times p times q divided by n. Well, some algebra involved here, but this really just simplifies to p times q, or we'll call it p prime times q prime divided by n. Alright, so I guess we should call this p prime also. All these are primes because we don't have a value for p, the population proportion. Okay, so what was p prime again? P prime is this. We might need q prime. Q prime would be 1 minus this, which is going to be 0.2. And then n is equal to 400. So the population proportion, the proportion distribution is going to be a normal distribution with a mean of 0.8, that's p prime, and a standard deviation of the square root of 0.8 times 0.2 divided by 400. So let's see if we can figure that out using our calculator. And with our calculator we can do this all in one command. Let's find the square root button. We have 0.8 times 0.2 and then divide by 400. So we don't have to worry about parentheses within the square root with a fraction because it's all multiplication. There's no addition or subtraction going on. And that gives us a 0.02, so that's our standard deviation. Okay, so that's part C, where it would be a good idea to use the population proportion. Alright, now they ask us to construct a confidence interval, a 95% confidence interval. I'm just going to go directly to the calculator for that. So our confidence interval in our calculator, what we're going to do is we're going to press our stat button and go to tests. And last time we looked at the z interval and the t interval. If you go a little bit past that, there's a 2samp z int and 2samp t int, and then we got the props now, prop z int and 2 prop z int. So for this particular problem we will be using one proportion, that's the one proportion z interval. So we'll go ahead and press that, and it's asking us for the x and the n. So our x and n are given over here, which is good. Our x is going to be 320. Our n is going to be 400. And our confidence level is going to be 95%, so that's good enough. And then we'll ask it to calculate, and we get our proportion. So it looks like we're between 7608 or 76%, less than our proportion that we're looking for, and 0.8392. So 83.9 or 84%. This is our confidence interval, and sketch the graph. If we were to look at the graph of this, we're looking at a normal distribution, and our mean is 0.8, and our 76% here, and our 83.9%. Oops, let's stick with the decimals here. And so this is the 95% capture, and you got 0.5 on a tail, which makes each tail to be 0.025. So if we were to calculate the error bound is going to be the boundary distance from point 8. So what we could do is we can just subtract this from point 8, or we can take the difference and divide it by 2. I think it's easy enough to subtract it from point 8. We can just, it's going to be 0.0, well, let's calculate this, 0.8392 minus 0.8. And then, so this is your error bound. So error bound for the proportion is 0.0392. There's other ways, let's take a few minutes here, or a few seconds, to talk about this. Several ways to write this. And once we have the error bound, we can write that our proportion is going to be about 80%, that's 0.8, plus or minus this 3 percentage points, or 4, let's call it 4 percentage points. So that's what the error bound is good for. It's good for stating things where we have the suggested, or the point estimate, the suggested proportion, plus or minus your error bound. Okay. Last one, if this survey were done by telephone, list 3 difficulties companies might have in obtaining random results. So this is going back to chapter 1 and talking about effectiveness and biases of the samples. So if we were to do this survey by telephone, the insurance company surveying, so by telephone, we might not get a good sample because only the people, it'll be a voluntary survey. So we might not get a full picture of this because the only people who voluntary, who would stick around and do a survey would be people who would be willing to sit there and talk and volunteer themselves. Also, you might miss the people that don't have telephones. I think everybody has a telephone nowadays, but that could be another possibility. Without telephones. And another difficulty in obtaining random results might be you might capture somebody who doesn't drive very often, or you're not guaranteed to capture people that actually drive on a regular basis. So might not, let's call it might not. Might not get drivers who drive often. So basically, just by a random surveying on a telephone, you might not get the actual population that you want. Okay, so this is exercise 11 from chapter 8, and I hope this helps.